I think you are muted.
Okay, yeah. So in this question, we have to figure out which of the following devices this addresses corresponds to. So for that, we have to do some bit of math. So we'll take this address. So by looking at this address, we can see that this is the closest address for this, right? And this address is a bit more greater than this address. So this 2 million, this corresponds to this interrupt controller, right? And the next 256 bytes will be corresponding to that. We have to figure out where this number comes. Okay, so we'll take this. I'll just then I'll do this. Yeah, I'll split the screen. It's fine.
Maybe you can download all of this and
Oh, this is fine. Yeah. Okay, then we'll do that. So if we write this in binary, we'll get the last 3 digits, right? We see 3, which is 1 1. We'll put 2 zeros behind, and that C, which is equivalent to A 10, B 12, 11, 12, right? 12 in this case, 8 plus 4, and D, which is 13, 1101, right? So we'll convert this into, so we have bytes 256 bytes, right? 256 bytes, which is equal to 2 power 8, right? So 2 power 8 will be 0, 1, 2, 3, 4, 5, 6, 7, 8, and this part. So which means at after the addresses after 1 and the things will lie between 2 power 56. It will be greater than 2 power 56, right? The addresses after this 1, and then we can see the next thing will be 2. Add one more thing. So if you add one more thing to this, like add another 2 power 256, it will be 512, which means this bit. So this after this timer, what will be there? So that range, the thing after this 1 and 0, this range will be for the keyboards, right? So now we have 1 and 1. So we need to add one more 2 power 8 here. Then it will become 1 1, right? So that address will correspond to the mouse. So since this 256 is 2 power 8, we'll add 2 power 8 to each iteration. So our address, so for address is starting from what is that, 2 million. Oh, I'm assuming starting from zeros, right? So if you add 1 2 power 8, it will be this. Eight, right? This is 2 power. Okay. 2 power 8 in the sense 0, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and 7 and 8. 7 and 8. This will be it in there, right? And this is our number. The number we have is 1, 2, 1, 0, 1, 1, 0, 0, 1, 1, 1, and 1. So we need this 1, 1. Now here it is the 0, 1, and we need 1, 1. So that if we add one more 2 power 8, it will become 1. This number will become, upon adding this, it will become 1, 0 and something, right? The remaining. And if we need 1, 1, so we add one more thing, one more 2 power 8, so that it will become 1, 1 and something. So we added only 2 power 8s, right? So upon adding 1 power 8, it will correspond to the timer, and upon adding 2 power 8, it will correspond to the keyboard. So this address would correspond to keyboard. And if you add one more 2 power 8, this will, if you add one more 2 power 8 over here, then it will become 0, 0, right? So that address will correspond to the mouse. So after adding 2 power 8s, you will reach this destination, and this destination corresponds to the keyboard, the interrupt controller. Then 1 2 power 8 will correspond to the range of timer, and the other 2 power 8 will correspond to the timer, this of the keyboard. Okay. Is it? Do you understand?
The alternate way to do this would be to just convert that to decimal, no?
Oh, the 3CD decimal and just add this to power 26, right? Yeah, if we could do that converting to decimal, that would be fine. So this method, that we are ignoring these things, right? Actually, we are only focusing on these 2 bits.
Okay.
So that's why converting decimal, this hex to binary will require some overhead, because you have to do 2 jumps, decimal to binary, and maybe this hex to binary, and maybe hex this to that. Or maybe I think you could also use that. If you have calculator, it would be easier, I think. So maybe I find this intuitive. If you, that could be also done.
Sir, am I audible?
Yeah.
We could also, just take the 3CD part along, because that's what's being added to the base of the interrupt controller, right? So, but
Sorry.
yes.
Sorry.
The 3CD, we can convert that to binary.
Yeah.
Sorry, convert 3CD to decimal, and then we'll get an idea of how much is being skipped.
Yeah, you can also get that.
Okay.
So I just converted this number to binary, so that so converting from hex to binary is easier for me, and converting this to binary is also easier, since it is a power of 2. So I just need to keep track of this. Maybe to get an idea in decimal, you can convert that into decimal.
Okay.
Yeah.
Check box on the chart.
Okay. So then, yeah, I'll zoom this a little bit. So we have this. You have to identify the correct statements from this, the characteristics of the baud register, RX register, and the status register. Okay. So all registers are 4 byte. So we'll see. So here this is the baud register. So this is an address, right? U16 means it's an unsigned 16-bit number, and that corresponds to this address of this UART base. So this baud register is a U16, which means it's a pointer to U16. So the baud register is a pointer, right? So in that case, this baud reg, since it's a pointer, it should have the size 4 bytes. And similarly, the status register, or these are pointers, right? In that case, the size of all the registers will be 4 bytes. Okay, but the value, like the value that the registers are pointed to, like this baud register, is pointing to some address, right? The 16-bit address. Okay, let's see. Yeah, the value present at this thing is a baud register. The value present at this baud register is of 16-bit size, but the size of the baud register itself is 4 bytes since it's a pointer. So all the registers present here are pointers, right? So they will have size 4 bits. Okay, and they are pointing to some values, different values, different integers of different size. Okay. Yeah. Then this is the stack computing stack pointer for the specific HART-ID problem. So here we have this HART-ID 3. So there is this formula for calculating the thing. So there will be stack. Okay, there will be this stack 0 in the memory somewhere around here, and each stack for the each HART-ID will be present like this. Okay, so here this is the stack 0, and here the stack pointer of the first HART-ID will be present here. Second HART-ID will be present here. This is for 1. This is for if there is a third HART-ID, right? So this is stack 0, and each of this is 4 KB, right? Then you can just say that the stack pointer, which is SP, for HART-ID 3 will be at stack 0 plus 3 into 4 KB, right? So here that answer will be stacked into 3 into 4 KB. So this 4 represents for 4 KB. So this will be the correct answer. Okay. Now we have this question. I think this was recently discussed in the chat space also, I think. Okay. How do I do this? Yeah, okay, yeah. This is sure why this is looking like that. They are zoomed. Now,
Could you go back to that first question for a minute? In that you said it is keyboard, no?
yeah.
But if you convert that to decimal and divide it by 256, you get 3.8. That means it will be mouse.
Okay, so maybe let's verify that again. We'll check that in both cases. We'll check with that also. So the number we have is 2 followed by. Okay, so the number we have here is 3 CD, right? We'll rewrite 3 CD again. 1 1 3. C it's 12, which is this, and then D it's 1 1 0 1. Okay, and 2 power 256 is 2 power 8. In that case, 0 1 2 3 4 3 4 5 6 7 8. Okay. Okay, so now this is the okay. So now the interrupt controller will be starting from this 2 million, the zeros things, right? After when we add a thing 250, okay, so the addresses beginning with 0 1 and these numbers are corresponding to 0 0 to that number are corresponding to interrupt controller, right? So starting from the 0 to this number that are corresponding to interrupt controller. From this number to maybe I'll write it here, 1 0 0, this thing will be corresponding to, looking at these digits, okay, will correspond to the timers, right? So adding up 1 KB. So this is this region 0 to thing will be interrupt controller, and this thing to that thing will be timers. And I'll put this range here, timers, and here it's interrupt controllers. And then you add one more one, which will give you, sorry, am I writing this wrong? Okay, you 0 1 0. Maybe let me clear this out and write it clearly. So we'll start with zeros. So all zeros will be the start of, we need 9 zeros. And here we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here is 9, 0. This is 8, 9, 10, right? So this is at the 10th place. 10th place that we have here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll have 10 zeros. Look at this. And that is 256s, 2 power 8, which means this. We'll be adding this one, right? And this all zeros will be corresponding to, so this range will be corresponding to interrupt controllers, and then 1 0 range will be corresponding, this range will be corresponding to timers, and 1 1 will be this range, the 0 to 1 1 will be corresponding to keyboard. Yeah, so the things greater than 1 1, which is this, right, will be after that. So this is 1 1 0 0 0, all zeros. Until this, it will be keyboard. Yeah, then after that, it will be mouse. So when this address 1 1, all zeros and that 1, this addresses from here, this all zeros to till a 2 KB, which is 1 0 0, it will be mouse. Yeah, I think, yeah, the answer is mouse, because starting from 1 1 0 0, it's mouse, right? Until 1 1 0 0, it's keyboard. Okay, yeah, that's correct. It's mouse. Okay, so in this case, we have 32 MB of physical memory and 32-bit virtual address system, and the page is up to KB. So the number of bits. So for this, we'll have to calculate. So 32 MB is converted into bytes, which is 32 is 2 power 5, right? 1 2.
Yes.
Yeah. Then 2 power 5 plus 10, which is 25. Then you have 32-bit virtual address space and the page size. So here, this is virtual addressing space doesn't mean anything, because the total size is there and the page of phone size is there. This is what you need to take into account. So there you have 2 KB, which is K means it's 10 and we have 2, then it will be 2 power 11 bytes. So totally the number of pages will be 2 power 40 pages. Okay. And similarly, this is kind of inverted question. You have the total space and the size of the page table, the number of entries in the page table, and total space. We have to find the size of the page frame. Okay. So it's like there is total number of spaces 4 GB. So this and this are now given. You have to find this, right? So you can just swap it and put it there and put it down. It will be a similar calculation, right? So 4 GB will account to 32 to power 32 divided by the size of the number of page table entries, which is 2 power 20, and you will get 2 power 12, which is 4 KB, right? Yeah, I think these both are the same. Yeah. Okay, so here, suppose a process is running and a timer interrupt occurs, the process will change into its state. So it usually change into runnable state because it's a stop due to a timer interrupt, so that it will change to runnable state. Okay, it will go into sleeping state whether it is waiting for a child process to exit or using a IO operation and waiting for the input, things like that. It will go into a sleeping state when it exists, and it's when a process exits, it usually goes to a zombie state, and after it the resources have been taken away, it will go back to unused state. Okay, so the state transitions will be like, maybe I could draw a simple state transition. So initially, some of before creating a process, an entry in a process control block, there will be a set of 64 processor in XPC system, for example. So there will be total number of this. So it will be in an unused state, this for this process. So it goes from unused, then some process will make it, some new process will be created. So this will be converted into a runnable thing, and the scheduler will schedule it, and then it will become a running thing. Here you can think of scheduler running, and it comes back to runnable state with timer interrupts, and timer interrupts. After the scheduler will schedule another process, and the running state will go to a waiting state, sleeping state, which is the sleeping state. For any system calls, waiting for a system calls, or waiting for system calls, right? The IO operations and things like that. Actually, waiting for a child process to exist, it's also done by a system call, right? Wait system calls. So it will go to a sleeping state then, and then it will be, and after sleeping, it will be set to runnable, and scheduler only will maintain the running thing, right? Anything that's sleeping, it will be awakened and made into runnable state, and scheduler will say which should be running. And when a process exists, exits from the running state. It will be in the running state and it will exit. It will become a zombie, and then the things will be recovered. Like the resources will be recovered. And it will go back to unused state. So this is how processes, the states of the processors grow in x86. And usually it's similar with other operating systems also. Okay. And one more thing is there is thing called orphan discussed, but that is not actually state in actually a state in a processes, but it is something that whenever a parent dies, the child process of that parent exits. The child process of that process will become an orphan, and that is not a process state. This will become a zombie since it exits, and this will become an orphan. Orphan is not a state, and usually we will reparent this to the init process, which is the first process. We will reparent this orphans to the init process. And now we have this UART bit reading question. So there is these things. What will the first 5 bytes from the right? Which means these bytes. So usually these bytes are the page table entries, bytes of the page table entry. So this is a valid bit. This bit is the readable bit, writable, executable, and user bit, the global bit, the other dirty page directory bits and things. Okay. Now we are focusing on the first 5 bits only, which means 0, 1, 2, 3, 4 until this U. Okay. So here, what is the first map? KV map, UART, page size, R and W, right? So we are setting that byte for R and W to be 1. So this sets that bytes to be 1. It's readable and writable. So what you can say, readable. Second one, the second bit and the third bit should be true, which is true in all cases. And the valid bit, it's the what happens to the valid bit is that since this UART is a valid thing, it should be automatically initialized to a valid thing. So it will be a valid bit, right? It will be initialized to a valid bit before using this memset operation. If you see this memset operation and this calloc function, when it initializes this, it will set that initialize it to all valid things, and this calloc will not set the user to this. Only the umalloc function will set the user bit to 2. So if you see, this question involves more knowledge about these two functions, like the calloc function. If we could see the calloc function. Yeah. So when calloc is called, it takes a page from the free list and calls the memset function, right? Now what's this memset doing? Okay. Sorry. Yeah, this memset is. So it's just filling with some number. So it's erasing the previous code that existed there. Okay, let's look into this code of this is KVM init, right? Center VM.c. Yeah. Okay. So the KVM map function. Yeah, that goes into this map pages. And this map pages, as you can see, sets the valid bit, right? That's how whenever the thing is doing it's the valid will be, but it will be set automatically sets, because it's implied that without the valid bit the UART cannot function, right? If the pages seem to be not valid, then it cannot perform the operation in that thing. So it should be made valid previously, and then the user bit will be false because it's a kernel page table. So that's also assumed. So in that case, the user bit will be 0 and the valid bit will be 1, and these two are the deciding factors of among these two options. So this will be the correct option. The valid, read and write will be true. Okay. Yeah. Then we have this syscall function. The return address of the A7. What this A7 has? The trap frame. So this TF is the trap frame for the process, this process, which is taken from the myproc. So usually this syscall is present in the kernel code, and when this happens, we'll set this A7 to the particular system calls value, right? So the value returned at A0, as you can see, when a system call happens, the value returned by the system call is placed inside this A0. But what does A7 has? A7 is the num. The tab frames A7 register is taken as the num, and it decides which system call to make, right? And there is this basic check. So there will be a set of system calls in this matrix. It's actually defined as an array of function pointers, to be precise. And this could see this is called function. It's in this is called.c. Yeah, you can see all those system calls are imported here, and that system calls are made into an array of function pointers. So this is actually an array of function pointers, system calls, right? So it's kept like this, and this is the index of that system call, and that is the system call itself, the function. So it will be a pointer to that function. So that number decides which functions to execute, which means which system call to execute, right? So that's why you can say that the A7 register is responsible for choosing the system call. So it's the number that identifies the system call. Okay, and A0 takes in the return value, what is returned by the system call. Okay, if it is there is an error between the system call, you will get an -1 in the A0. Okay. Okay, so which of the following sequences of the steps determine the order of allocating process structure for the init code? So we have to create, this is the process structure of the user init function. Okay, so let's see this function of user init. So for that, we'll start from the main. Go to the first user process. Now you can see what are the steps that being done. So this alloc proc is being called, right? So what is that? Alloc procs allocates the process from that process page table and things. You could see this alloc proc function takes one unused state from the process table. This process table takes from that. So we first take a unused process. Okay. So what will be the first step here? Okay. Okay, we'll take the first, this is the first process, right? So we will take the first process. That step is not included here. Right? In this case, which means after we call alloc proc, okay. After we call alloc proc, we copy the instructions of the init code to the user virtual UVM init means we are initializing the user page table. Is that there? Okay. This is the first process, right? Into this. We are looking at the user init function, right? Yeah, this alloc proc. Yeah, here is the things, I think. Yeah, here is what we got. This alloc proc is getting called, right, when we are finding that. So we are finding this unused state, and then here comes the step. When we go to found this state. When we found an unused state, we go here, and here comes the path. Then we allocate the process ID, and at first the process PID will be is 1, right? It will be starting from 1, and so that will be the first process. So we set PID is equal to 1, so this comes, this will be the first thing, And then we allocate the process PID, and then we allocate the trap frame, which is this. Okay. This is setting up the trap frame, right? Yeah. So this one first is the first one, and the 6 is the create the trap frame is the second one, which means we'll be looking at these two of the options. And then after creating the trap frame, now we just got our trap frame, and we create the page table for the process. And then we set up this context switching things, like the return address will point to forkret, which means after this allocation is done, this process will go into the scheduler, and this forkret, when the scheduler try to execute this process, since we make it usable, it will return from the forkret. Okay, this function, the first user process, will return from the forkret, and the stack pointer will be pointing to this. So here, after the page table, third one is the page table. So here it's not mentioned, the page table is not here. So the third one will be in this order. Allocate the trap frame, the page table, then set the process context, allocate the context. So the third one will be setting up the return address here. So setting up the return address to the forkret, and after that we start pointer, stack pointer, right? So 3 after, then 2. It will be at the last. And before that, we are mapping the trampoline and the trap frame. Where is it? Inside the proc page table, I think. Yeah. Here we are mapping the trampoline and the trap frame. This map page table, we create the map, set these initial mappings, so that the user's page process will be able to trap out of it. So these parts are required for the context switches, right? So we set up the trampoline, which is the highest thing, and after that we'll set up the trampoline, which is below. So here we set the process ID, then we create the trap frame, then we create the page table. Inside, creating the page table, we'll create map the trap frame and the trampoline, and then the trap frame, and then we'll set this return address and the stack pointer. So it will be 1, 6, 4, 5, 3, 2. 1, 6, 4, 5, 3, 2. This. Okay. Yeah. Here, the correct sequence of setting up the thing. So this is the high level view. This thing. So this also kind of similar to that question. We found using this, we found a unallocated proc structure, and then what we did, we created a tab frame and a page table, and then set up the context. It's a high level question. That's more of a deeper level question. This is the same question, but in a higher level. Then we create a trap frame, and then a page table, and then the context. Okay. So it will be 1, 3, 2, 4. 1, 3, and 2, 4. This will be the answer. Okay. So this, if a parent process terminates before its child process, which process are not the output process? This we have seen, it's the init process. Then we have this question. Process P1 that forks process P2, and P2 forks P3, and P3 forks P4. P1 and P2 continue to exit while P3 terminates, and now P4 also terminates. Which process must wait for the and reap P4? So we'll see this. We have P1 that forks P2, that forks P3, that forks P4. Okay. Now P1 and P2 continue to exit, and P3 terminates. Now, when P4 terminates, which process must wait for and reap the P4? So now you can see when this P3 terminated, P4 is reparented to this P1, right? So this P1 will wait until P3 terminates. So that process is P1. Okay, no. It's not P1 actually. It will be reparented to the init process, right? Init process, not P1. P1 maybe some other process which init have forked. Since all the process are the process which init has forked, P1 will be some of that process, and whenever this is reaped, the init process will take. Okay. So this is kind of the same question as this, but in a different manner. Okay. So daemons are deliberate orphans process that became detached from the user to operator. Yeah, that's true. So there are some cases when a process fork and create a child and it exits voluntarily. Then this will automatically become a daemon. This is a kind of daemon. If P3 has voluntarily existed, if it's an involuntary, it is not called as a daemon. It's a general orphan. So daemon is a subcategory of orphan. Okay. Any doubts? Then
So if you have any doubt, you can ask the question. Otherwise, we will bind up the session.
Could you solve practice assignment 2, question number 10?
Okay.
You're on mute.
Oh, okay. Sorry for that. Okay. So we have this 2-level paging system. So the page size is 8 KB and the page table entry size is 4 bytes. This is the outer page table is 4 KB. Okay, page size is 8 KB. This one page. So if page size is 8 KB, the offset widths, right? There is this offset widths. The page offset bit should be able to address these addresses inside a page, right? So the offset bits, the number of offset bits must be equal to which is 2 power 13, right? Which means we need 13 bits to for the offset in the virtual addressing space, right? This is 13 bits. Totally we have 4 bytes. A page table entry. So the page table entry is 4 bytes, right? So what can be the maximum size of the virtual address space? So our virtual address space will look something like this, and here we'll have the outer page table entry and the inner page table and the offset, right? So this is the L1, L2, we'll call it like this, right? Or L0, L1, L0, L1, B. You can consider anything, right? So we have this 13 bits offset. We need to find what is the maximum size of the, what can be the maximum size of the virtual address space. So this is our virtual address space, right? So now at least minimum there need to be 13 bits. So what are the other parameters? We have 2 levels of page tables. So this is the outer size of the outer page table. We have given the size of the outer page table, and each page table entry is of 4 bytes, which means this outer page table will have entries of 4 bytes, right? So how many entries this can have? 4 KB, which is 2 power 12 by 4 bytes, which is 2 power 2. This means it's 2 power 10. So this outer page table, how much it can have? 10 bits. And so this is the size of the outer page table, which means we can have 2 power 10 inner page tables, right? And each inner page tables, now we have to find this part. Okay, what do we have? Page table entry size is 4 bytes. Since page size is 8 KB, which means our second level page table can have the maximum. So each page table must be within a page, right? Each page table itself must be within a page. Since our page size is 8 KB, our second page table, the second level page table can have the maximum size of 8 KB. So we are talking about maximum, right? This can be 8 KB. So then how much it will be? 11, which is 2 power 13, right? 2 power 2. Since each page table entry is 4 bytes, here also it will be 4 bytes, right? Think it like that. So this is 13 bits. So the maximum is 10 plus 36. Sorry, am I doing something wrong? Offset is 13. Okay. Outer page table. Okay. So the inner page table, outer page table is of 4 KB and 4 bytes. So it can have, okay. This is 8 KB, right? 8 KB. Oh, this here we have 2 power 2. Yeah. I missed this 2. I just wrote that 13 down. It will be 11, right? Yeah. Now this will be 34. Okay. I forgot to cancel this out. So this is how this is the maximum size of a page table we can have, right? Since the page size is 8 KB, max size of the page table is also limited to 8 KB. So we cannot split a page table in 2 pages. Okay. So that realization helps us to find this number. And what is the maximum number of page directories we can have? Since this is that, the size of the outer page table is this. We can limit the maximum size by this piece. So our whole virtual address space can have this much addresses. That's the maximum size of the virtual address space. Okay. Make sense?
Yes.
Okay. Any other doubt?
So the clarification that you said it will be shared regarding the last question of the second grade assignment. I could not attend the previous session, so if it was done, then I'm not sure. But
What question?
so the last question of grade assignment 2 on
This one?
on one of the
That last question, right?
yeah, yes sir.
So in that we have given marks to all. Like I think it will be like given in the dashboard also. Like because there is some ambiguity is there. So like I think this question prepared by I think some professor TA. So we are not able to find out the what is the actual like what is the actual ambiguity in this question. So
Okay.
it will be given marks to all.
So when you say marks, you are like everybody will get full marks or partial or something.
Yeah,
So there's a
everybody will give full marks whatever the marks is given.
okay. So I mean, I as of now in the dashboard I see that marks for all the grade assignments have been released except for this one for grade
Okay,
assignment.
maybe like we'll check and we'll release as soon as possible.
Okay, sir. Sure.
Okay. Okay, then if you don't have any doubt, all the best for the quiz 1 exam. Do well.
Yeah. Thank you, sir. Can you release the link for this recording because I
Yeah,
joined in a bit late.
I will upload in the YouTube.
Okay. Sure. Thank you.
Okay, thanks everyone. Thanks for joining.
Thank you.